Hello. In this video, I'll be talking about section 10.1 on parametric equations, and this is actually a very long section in terms of things worth covering, so I might break this video into smaller parts. So here's the idea. We are very used to presenting curves in terms of x and y. Usually y is a function of x. Sometimes we simply have an equation with y and x related to each other, as we saw in implicit differentiation. But there are other ways to think about a curve that are sometimes more natural, and that's to think of x and y in terms of a third variable called a parameter. And it's very helpful to think of the parameter as measuring time. Right? Imagine we just had something moving around, a particle moving around the plane. And you could imagine that it's tracing out a certain path. Now, under most circumstances, the path it traces out probably would cross itself. Y would not be a function of x. And it could be very hard to describe this path once we're done with some simple equation with x and y. But instead, we can think about x and y independently. As I move around, no matter what time it is, if I stop at a specific time, wherever this particle is, it has one specific x coordinate. So if we're just thinking about the horizontal position, right, it goes up and down, but it also goes back and forth. There is theoretically a function which tells us at a given time what is the x coordinate. And similarly, there's a different function that says at a given time what is the y coordinate. So instead of thinking of y as a function of x, we're thinking that both x and y are functions of a third variable called a parameter. And again, often we think of it as representing time if we're thinking of motion. So let's look at an example. Let's imagine we have a circle that's moving along a linear diagonal path. And then let's also imagine that that circle is spinning as it moves. So I actually have this set up on Desmos. So here's our circle. And you can see there is a point right now at the bottom of that circle that I have highlighted. And let's imagine that the circle is moving along a diagonal path and spinning at the same time. Where would that point go? So I have this, I'm doing it a little bit slowly. The circle is moving in a diagonal path, and the point is spinning around as that happens. So theoretically, there is a function that would just keep track of where the x coordinate of that point is. We would get that by, on the one hand, thinking about where is the center of the circle, on the other hand, using some trig to figure out where the point is compared to that. And we do the same thing with y. There's one function that explains what the x coordinate is at a given time. There's another function that explains what the y coordinate is at a given time. And for this example, you can see I already have these listed. And if I turn this on, this curly Q is actually the path that that point would take. It's not as obvious now, but as we move along, right, we were thinking, okay, it's spinning around the circle while the circle is moving. And it turns out the path it follows would look like so. This graph in red would be very hard to describe just in terms of x and y. Certainly y is not a function of x. Trying to do it another way is very complicated. But we have a situation here where we have this formula like so, that's not super complicated, explaining what is the x coordinate in terms of time. And we have this one over here explaining what the y coordinate is. So now that we have some idea of how these parametric equations work, that's the phrase we usually use here, parametric equations. There are various calculus questions we might want to ask. And so here are 5 of them that I'll be addressing in this section. So the first is if the parameter represents time, and we're thinking of these equations as giving us the position of the particle, what is the speed at any given time? We might also ask how long is the arc of a parametric curve between two specified points? But if I have my curly Q like before, right, what is that actual distance as I travel along the curly Q? And again, if we're thinking of this in terms of motion, arc length is the same as distance traveled. What is the direction of the curve at a specific point? So if I have some point on my curly Q like so, and I want to know, in what direction is the particle moving at that moment? Well, we could liken that to slope of a tangent line. Right? As my particle is moving around, the slope of the tangent line kind of gives us a sense of the instantaneous direction. Right? So it's really just slope, but it can represent direction if we're thinking of it in terms of motion. We might want to figure out what's the concavity. And then finally, could we find an area underneath the curve? Right? So we're not really going to talk about an area inside the curly Q, although that would be really interesting. We would be thinking more just sort of traditional. If our x-axis is down here, what's this area underneath the parametric curve? So we'll get to all of these. And for some of them, I won't be giving you a full proof, but I'll be giving you a gist of why these formulas are correct. Okay, so our first one here is instantaneous speed. So let's imagine approximating instantaneous speed with average speed. So we have a particle like so, moves along this path, and maybe here is where it is at one time. And here is where it is at another time. And we basically want to figure out what is its average speed. So we could approximate the speed. So I'm sorry, we're trying to find average speed. So average speed is distance divided by time. Here we're going to cheat a little bit and think about displacement instead of distance. Don't really worry about this. I just want to give you a sense of where this formula comes from. Right, so we can think of this as sort of an estimate of distance. And imagine we're drawing a little right triangle like so. X changes a certain amount, and Y changes a certain amount. So our approximation for the distance there would be the square root of delta x squared plus delta y squared, just by the Pythagorean theorem. And then our average speed would be approximately this distance divided by this change in time. Now, let's try to tie this to x and y separately. So x is a function of time. And we're assuming that x and y individually are differentiable functions. So the instantaneous rate of change for x would be x prime of t. But that would be approximately the same as the change in x over the change in time. This is the average rate of change just for x. This is the instantaneous rate of change just for x. And we can do the same thing with y. So here's actually what we're going to do. This thing we have over here, I'm actually going to think of it as this. Change in x squared plus change in y squared. And then I'm going to write change in time as the square root of change in time squared. And then by properties of radicals, we can just do it like so. And then I can break up that fraction. And then what we have in parentheses here is the average rate of change for x. That's approximately the same as the instantaneous rate of change. And we can do the same thing with y. Now I'm waving my hands a little bit about why this is okay, even though we're approximating. There are limits hiding in the background. I don't want to worry about that. But here is our instantaneous speed formula. It is the square root of the derivative of x squared plus the derivative of y squared. This is assuming that x and y independently are differentiable functions of time. If we know which function gives us the position for x and which function gives us the position for y, if you want to know the overall rate at which the particle is moving, that's your speed formula. And now once we know speed, we can go to arc length. Even if our curve was not presented in terms of time, we could pretend that it was. And if we have some particle moving around and following some path, if we're imagining it as motion, then the length of this curve is the same as the total distance traveled. Total distance traveled is the same as the definite integral of speed. This is the one-dimensional version that you already learned in Calc AB. Speed is the absolute value of velocity. If we take the definite integral of speed, we figure out how far we have moved in terms of total distance traveled. Here, it's exactly the same principle. Total distance traveled is the definite integral of speed. So arc length, which is the same as total distance traveled, is the definite integral from a to b, and these are in terms of t, of our speed formula. Derivative of x squared plus derivative of y squared, all under a radical. So let's do an example. So for the example we just did, let's first find the speed of that point when t equals pi, and then find the total distance traveled by the moving point over the course of the first 5 seconds. So just going back to what this looked like, if a equals approximately pi, when we're at that point, how fast is the particle moving? And then also from 0 to 5, I could actually just change that here. How far does the particle go? Right, so I'm cutting it off there from 0 to 5. What is the total length of that curve? And we'll use a calculator as appropriate. So let's just remind ourselves, here, where are our formulas? Here they go. So to figure out the speed, the rate at which x is changing. So this is basically, you could think of this as measuring horizontal only velocity. Hopefully I'm not doing this wrong. So derivative of 2t is 2, and then the derivative of cosine 5t by chain rule is negative sine of 5t times 5. Derivative of y would be 1 plus 5 cosine 5t. So now, if we plug in pi, hopefully this is not too awful. If we plug in pi here, we would have 2 minus 5 sine of 5 pi. Sine of 5 pi is 0. If we plug in pi here, 1 plus 5 of cosine 5 pi. Cosine 5 pi is -1. So this is 1 minus 5, which is -4. And so our speed at that particular time would be the square root of the rate at which x is changing squared plus the rate at which y is changing squared. So that's root 20, and let's just get a decimal there. It's about 4.5, about 4.472. And I don't have units on this. We're doing this in just pure units. Now to find total distance traveled, it would be the integral in this case from 0 to 5 of the square root of, so here we're not going to do specific numbers, we need these formulas. This is x prime, and we'll square it. And this is y prime, and we'll square it. We'll ultimately need a calculator here, but let's actually see how nice this thing is. I'm going to add a page. For these kinds of things, more often than not, we're using calculators, but sometimes it's worth seeing whether these things simplify. We'll get at least some simplification here. If I FOIL out the first part, I would have 4 minus 20 sine 5t plus 25 sine squared 5t. If I FOIL out the second part, I would get 1 plus 10 cosine 5t plus 25 cosine squared 5t. And what happens, at least in this case, is here we have 25 sine squared, and here we have 25 cosine squared. So these together are actually equal to 25, because sine squared plus cosine squared of the same angle is 1. So when we combine that with the other constants, we would have a 4 and a 25 and a 1, so that's 30. And then minus sine of 5t and plus 10 of cosine 5t. And let's just, before we get a number here, let's just see what would be plausible. Go back to the graph. So we're starting here around 1, 0, actually literally at 1, 0. And we finish at about 11, 5. So it goes over 10 units and up 5 units, right? So that distance is, maybe 11-ish. And then when we add the curly Q, I'm expecting an answer. I want to say the answer is going to be 13 or so, right? Somewhere in that ballpark, maybe a little bit bigger, maybe more like 15, right? But it's bigger than 10, but not like way, way, way bigger than 10. Let's see what this actually works out to. I'll put this in my calculator, which is about to lose battery. So the square root of 30 minus 20 sine of 5t plus 10 cosine 5t. Let me just double check that I have typed this in correctly. Obviously you can't see. And I put that in. And, oh, I'm getting a warning message, but this is coming out to approximately 26.253. That was bigger than I was expecting. But perhaps I was wrong about my estimates. Perhaps the spinning around really adds a lot more than I realized. Yeah, I guess so. All right, fair enough, right? Sometimes our estimates of these things are not quite right. But going back here, yeah, I guess the curly Q makes it about twice as long as if it did a straight line. I now find that somewhat believable. All right, now don't worry about needing to simplify all the trig sometimes, but you do need to make sure you know the relevant formula, right? There's our arc length formula, and that you can put it in your calculator very accurately. So what have we covered so far? How do we calculate speed when we have parametric equations? Now, we're just in 2 dimensions. 3 dimensions is very much analogous. It's not covered in this class, but I think you could imagine if something were moving in 3 dimensions, as things often do we see how we could extend these formulas? I think it's pretty obvious. All right, what else can we talk about? Oh, we have another example here, and then maybe I'll stop the video before we get to slope. Another very famous example of something that is given in terms of parametric equations is a kind of graph called a cycloid. So it's a little bit similar to what we already saw, but now let's imagine that the circle is not moving diagonally, it's actually rolling along the ground, and we're following a specific point as it rolls. So I have this set up. So here, the circle is rolling, and we have a point that is on the circle, and it only spins around because of the roll, right? So before it was like it was flying through space and had spin on it. Here it's just rolling. And one can compute that the parametric equations for that specific point would be this thing up here. Right, so it looks a little bit like a series of semicircles, but this is not literally a semicircle. This shape that we get is called a cycloid. So, assuming the circle has radius 1, which we'll do in our example just to make things simpler, these are our formulas for the x and y coordinates for that cycloid. And in this case, we're just going to make the angle theta the parameter. Right? You could imagine that it's rotating at 1 radian per second, if you want to think of that as the same. It doesn't really matter. Right? Whether or not we are rotating at a constant speed, or we could be rotating in a way that's kind of jerky. It goes fast, and then it slows down a little bit, and it goes fast, and it slows down a little bit. We'll get the same curve, regardless of what happens. We don't really need to think about the time. As long as it rotates through every angle eventually, we get that curve. So that's why in this case, we're just using theta as our parameter. Imagine it as time if you like, it's unnecessary. So let's figure out what is the total length for arc length for one full spin of the circle. Right? So that would be 2 pi. And then we'll just evaluate that by hand. It turns out that if you are very clever, you can make some substitutions. But let's just see what we can do by hand and then have the calculator finish. So our arc length here for one full spin, arc length, would be the integral in this case from 0 to 2 pi of the square root of x prime of theta, in this case, squared, plus y prime of theta squared, d theta. So our first derivative, here I mean the derivative we do first, so that would be 1 minus cosine theta, and the other would be sine theta. Derivatives here aren't too bad. If we FOIL this out, we get 1 minus 2 cosine theta plus cosine squared theta. And then here we have sine squared theta. So as before, that trig identity will be helpful. The thing I've underlined is always equal to 1. So we're actually integrating 2 minus 2 cosine theta. Now there are very clever ways of doing this by hand. Let's not worry about that right now. And let's try to estimate this from the graph. Now before we had this circle that was spinning really, really fast. Here the circle is only spinning as it rolls. So between the endpoints of any one of these arcs, the horizontal distance is 2 pi. There's some up and down to this, but it's not going to be double, right? If you were to imagine this like the circumference of a circle, then the radius would be pi, and half of the circumference would be pi times pi, which is around 10. Right, so just to have some idea of maybe a reference number. It's not a semicircle because we notice its height only goes up to 2. Right, so it's going to be a little bit less than 10 most likely. Here's what's really interesting. And again, you could do this by hand if you're super clever or have learned a lot of tricks. If I just ask my calculator to do this, the integral here from 0 to 2 pi of the square root of 2 minus 2 cosine theta. If you want to type theta, you hit the button with the pi in it. If you're just putting it in your calculator, you can give it another name as long as you're consistent. And this is exactly equal to 8, which I find a little bit fascinating. We have this thing that's very circular. It feels like there should be more pi involved in this answer. But it turns out that the distance traveled is exactly 8. Now, this curve called the cycloid, if we turn it upside down, it actually is a really interesting curve. It solves 2 famous math problems from several hundred years ago called the brachistochrone problem and the tautochrone problem. This word brachistochrone, means shortest time, and this means equal times. So here's the idea behind the brachistochrone problem. Imagine that, say, here's the ground, and we have a marble or something right here, and we want to get it to this point on the ground. Obviously, you could build a diagonal ramp, and then you could release your marble here, and it would roll down this diagonal ramp. Right? That's the shortest distance. Just make it go diagonal, and the marble will roll down and get to that target. That's the shortest distance, but it's not necessarily the fastest time because of how gravity works. It turns out that the most efficient path, if we want to minimize time, will be a curve that looks something like so. It's a little bit longer than the diagonal. And what will happen is the marble, because originally it's going almost straight down, it gets a lot of benefit from gravity and will accelerate very quickly, which will allow it to go fast when it turns around. And the shape that does this most efficiently turns out to be that cycloid we saw, only upside down. So an upside down cycloid solves the brachistochrone problem. If you want to get your ball from here to here, using gravity to make it get there as fast as possible, right? Not the shortest distance, but the quickest time. Put it on a curve like this. And then what also is satisfied by this curve, which is less obvious. If on this curve I had a second point right here, and I released them at the same time, this one has a shorter distance to go. So you might think it always has a head start, right? It has a head start, and this blue one will always be behind it. Well, it turns out that even though this lower point has a shorter distance to go, it's not getting as much oomph out of gravity. This one is getting more assistance from gravity. So even though this has the head start, it turns out that when this one slides down and when this one slides down, they actually get to the end at exactly the same time. Along this curve, it doesn't really matter where you start. If you start way over here, you're really close, but you're going to roll really slowly because you're not getting much help from gravity. All of these points will arrive at the same time. That's the tautochrone problem. The same curve has both of these properties. And you can actually find some YouTube videos where you can see how the inverted cycloid gets the particle there faster than a diagonal round. And you can also see examples where two marbles are released at the same time, and it's a tie in terms of getting to the end. It's kind of fascinating. Okay, let's pause because we've already done quite a lot of this video, and we'll do the second part in another video.